Let's talk about dosing. Dosing is determining how much of a medicine to administer to a patient. Essentially, it's a conversion. We're really converting a 200-pound patient into the 100 milligrams of medicine that they would need. Or we're converting an 150-pound patient to the 75 milligrams that they would need. Many people like to use the proportion method for dosing, but you should not rely on it. It's okay for the simple ones. If you're asked to find the dose for a 150-pound patient and the dosing is 2 milligrams per pound, we can set up a proportion of medicine to patient weight. So we would have 2 milligrams per 1 pound, and we could find out what milligrams we would need for a 150-pound patient. We could solve for that and get that X is 300 milligrams, and that would be the dose. But this doesn't tend to work for the more complex reality that we have with divided dosage. For instance, if I ask you to find the dose for a 150-pound patient, if the dosage is 2 milligrams per day in divided doses every 6 hours, it's no longer clear what thing I should put on the top, what two things I'm making a proportion of, because there are many things. We have the patient weight, we have the medicine milligrams, we have the day, your time in there, both in day and in divided dosage. So it's much harder to do. The better method to use is to use dimensional analysis. And dimensional analysis is a method of converting between two or more different properties using relationships between the two properties, also called dimensions, as conversion factors that have a value of 1 and therefore can be multiplied by a measurement without changing the original value. All right, let's go back and review some. You can't just multiply a measurement, let's say our measurement was 1.93y, by a number because it changes the value. I can't just multiply it by 7, then it becomes a different number. But I can multiply it by 1 because any number multiplied by 1 remains the same number. So 1.93y times 1 is equal to 1.93y. It's the same value. Remember also that ratios or fractions that have equal numerator and denominator have a value of 1. So this is also the same thing. 4 over 4 has a value of 1 as a fraction, and therefore I'm really multiplying by 1. 1.93y times 4 over 4 is equal to 1.93y, same value. If I knew a relationship between y and x, I could use it to relate this 1.93y to x. So I have the known relationship, x is equal to 3y. And now I take 1.93y and I multiply it by a ratio where the top and the bottom are equal, because in this case my relationship tells me that x and 3y are equal. Note that when I multiply it through, my y's will cancel out and I'll be left with 0.64x, which has the same value as 1.93y because I didn't do anything except multiply 1.93y by 1. Okay, let's go over this one more time because it can get tricky once we start putting in units that we're more used to. So again, we talked about applying the definition, which was that we're a method of converting between two different properties using a relationship between the two properties. In this case, my relationship between the two properties is that x equals 3y. In ours, we're not going to tend to see x and y. However, when we see units like milligrams and kilograms, they're going to be treated as if they were a unit, as a variable, and if it were in algebra. Also, when we did our final conversion and we had that ratio of x to 3y, that was called our conversion factor. We said we have multiplied using conversion factors that have a value of 1 and therefore can be multiplied by a measurement without changing the original value. This has a value of 1 because due to our known relationship, x and 3y are equal values, and a ratio with equal values on the top and the bottom have a value of 1. All conversion factors must have a value of 1, so they always have to have equal quantities in the numerator and the denominator. Note that this method works. It was successful because we've now previously had a measurement that was previously in terms of y, 1.93y, and now it's in terms of x, 0.64x. So I've converted from units of y to x. The general steps for dimensional analysis conversion or unit analysis conversion is that we begin by writing the starting measurement with units on the far left. Then we're going to write the desired units, the ones we're trying to convert to, on the far right, and that's going to guide us in setting it up. Then we're going to write conversion factors. Now these conversion factors will just be the units. If the units are going to cancel to get me from my starting units to the desired units, then I will have a strategy in place. Note that also the units that I put on the top and the bottom of the conversion factors ought to be ones that somehow I can find some equality or relationship. I'm going to use given information. It might be in the problem, it might be on a textbook table, to fill in those relationships into the conversion factors. And then I'm going to multiply all the numbers on the top and divide by all the numbers on the bottom. Okay, conversion factors must relate to things or to units. Study the word problem carefully. Words like per and percent or in every are relating to things. By the way, if it's a conversion factor that you find in the word problem, that's generally not the measurement you want to start with. So if you can identify the conversion factors, the one that's left over is usually the starting number that you're trying to convert. Sometimes your starting measurement can actually be a conversion factor also. One more hint. You want to set up the units first. Put the units into empty conversion factors that you think you could find a relationship between. Let's take a look. Which of these things that would be reasonable conversion factors I might be able to find some information for? The first one, meters per pound. Well, meters is a unit of distance and pounds are a unit of mass or weight. That's pretty unlikely I'm going to find that information relating those two things unless that information was given to me in my problem. The next one is micrometers and meters. That's pretty likely, and that's essentially a metric conversion. I can find out what the metric prefix micro means on a table and convert micrometers and meters. The last one is meters and seconds. Meters are a unit of distance. Seconds is a unit of time. On first approach, that seems a little funny. Maybe I can't, unless I remember that distance and time are really related by speed. If I knew something about the speed of the problem and I remember that speed relates distance and time, I probably could find that kind of information. Finding the hidden conversion factors given to you in the word problems can be a little tricky, but there are some key words. If you're given anything about an equality, you see something in parentheses saying something is equal to something. That's telling you how two units are related. If you see the word per officially means to divide or make a ratio, and it's really relating the two things. The per is relating the thing that was written before the per to the thing that's written after the per. If we're told 37.9 grams fluorine per 24.3 grams of magnesium, that's saying that 37.9 grams of fluorine per, and I'm going to put that as a dividing line and then move to the bottom of the fraction, 24.3 grams of magnesium. One of the nice tricks about our conversion factors being equal to 1 is that means that since the numerator and the denominator have equal values, we can flip them if it's a more useful conversion factor. So another conversion factor that might be useful in my problem would be 24.3 grams of magnesium per 37.9 grams of fluorine. Also, don't forget that cent is a prefix for 100. 15.9% abundance of sodium 21 means that I'm relating 15.9 to 100. In this case, 15.9 sodium 21 atoms per 100. In this case, we'd have to know something about what abundance means, but to all the sodium atoms. Similarly, if I was told 15% sodium chloride solution by mass, I know it's 15 per 100, but I have to be careful of what is the part and what is the whole. All percents are relating part on the top to whole on the bottom, unless I've flipped them later on. So the part in this case is sodium chloride. The whole is a solution. A solution is a mixture of two things. And then the by mass indicates the type of units I'm allowed to use. In this case, I can use any mass units as long as it's the same on the top and the bottom. So I could say 15 grams of sodium chloride per 100 grams of solution. Once again, if it's more useful, I could flip that conversion factor and use 100 grams of solution per 15 grams of sodium chloride. Let's look at a specific example. A recipe calls for 3 pounds of lemons. If an average lemon has a mass of 65 grams, how many lemons are needed? Let's break it down, look at the problem, figure out what do we need to get, what things are the problem giving me, and are there any clues in the problem? I need to get number of lemons. It's asking how many lemons are needed. I'm told that I have 3 pounds of lemons. I'm also told an average lemon has a mass of 65 grams, or 1 lemon is 65 grams. Note that when they're relating the lemon and the grams, that's a relationship. That can be my conversion factor. And once again, we said that the things that are the conversion factor are usually what we don't want to start with. That leaves 3 grams as my starting number. 3 pounds is my starting number. So I would put I need to figure out the starting number and the conversion factor, which we've done. The starting number is the 3 pounds. The conversion factor can convert grams to lemons. So I have a strategy in place, except for the fact that I need to get pounds to grams. And by writing it out this way, I can kind of strategize that I need to go from pounds to grams and then from grams to lemon. That would mean that I'm going to need a relationship between pounds and grams. Now I look up that 1 kilogram is 1,000 grams. I also look up that 1 kilogram is 2.20 pounds. So now I have 3 things that are equal to each other. 1 gram is equal to 1,000 grams, which is equal to 2.20 pounds. Okay, we begin by putting our starting number on the left. And then I'm going to begin, I should have written my desired units of lemons on my right. Okay, so I know that I have to get rid of the rid of the pounds. So I'm going to put the pound unit on the bottom of the conversion factor. I'm going to put grams on top so that I can convert 2 grams. My next conversion factor would have grams on the bottom because, again, now that I'm in grams, I would need to get rid of the grams, and I want to get to lemons. And I know from my above relationship that I can relate grams and lemons. And that will end up getting me units of lemons because the pounds will cancel out, the grams will cancel out. Now I can work on filling in the relationship, grams and pounds. Since 1,000 grams is equal to a kilogram and a kilogram is equal to 2.20 pounds, I can put 1,000 grams is equal to 2.20 pounds in my first conversion factor. And in the problem, we were told that 1 lemon is equal to 65 grams. Now I can multiply 3 times 1,000 times 1 and divide by the quantity that's been pre-multiplied together of 2.20 times 65. Or I could do 3 times 1,000 times 1, divide by 2.20, divide by 65, because 65 is on the bottom of the fraction. And I would get 20.97 lemons, or 21 lemons. How many kumquats are there in 14.2 glyphs of xenol? There are 35.7 glyphs per gander of xenol. There are 1.35 times 10 to the 14th kumquats in every gander. This problem shows us that we don't even necessarily need to understand what these units are. We can use this strategy regardless. Even though they're very bizarre and on a first reading this looks very scary, let's break it down. Okay, how many kumquats? That's what I need. That's what I'm going to try to find. I know that I have 14.2 glyphs of xenol. I'm also told 35.7 glyphs per gander. That magic word per is reminding me that this is relating glyphs and ganders. I'm told 1.35 times 10 to the 14 kumquats in every gander, and that in every is also a word that's sort of relating kumquats and ganders. That per is a magic word, and that in every is a magic word. Okay, so summarizing, we have that we're given 14.2 glyphs, 35.7 glyphs per gander. Note that I've changed it to a fraction now, and 1.35 times 10 to the 14 kumquats equals the gander. Again, that per suggests the ratio, and the in every suggests an equality. Both of those are my conversion factors. That means my 14.2 is my starting factor. So I'm going to put my 14.2 on the left. I'm going to put my units that I want to get to, kumquats, on the right, and I'm going to start strategizing my conversion factors. The first conversion factor ought to have glyphs on the bottom. I look back to the problem and I say, okay, what kinds of things can I relate glyphs to? And I see the conversion factor that's relating glyphs and ganders. So I'm going to put gander on the top. That means my next conversion factor should have gander on the bottom. Again, I look back to my problem, what can I get ganders to? And I notice, coincidentally, that I can have relating ganders and kumquats. And Zumquats is the unit that I'm trying to get to. So my strategy is in place as long as I can find the numbers to make these conversion factors equal top and bottom so that they're legal conversion factors. In this case, the problem told me that there's 35 glips per 1 gander. Note that in this case, the 35 is actually going on the bottom and the 1 is going on the top. If I had written that as the original conversion factor, I flipped it, but I'm allowed to do that. It's relating the two things and they're equal quantities. And 1.35 times 10 to the 14 Zumquats per 1 gander. And when I multiply 14.2 times 1 times 1.34 times 10 to the 14, divide by 35.7, divide by 1, I get 5.37 times 10 to the 13th Zumquats. Okay, let's look at one where it's got several conversions. A car gets 35 miles per gallon of gas. The density is 0.75 grams per milliliter. How many miles can the car travel on 76.5 kilograms of gas? So it's asking for miles. We're given a conversion factor between miles and gallons, 38 miles per gallon. We're told a conversion factor for density, which converts mass and volume, 0.75 grams per milliliter. And we're told a weight, 76.5 kilograms. So the first two of what we're given are conversion factors. The kilograms would be our starting factor, and we're trying to get to miles. So we know kilograms must be on the bottom of the first conversion factor. We also know that miles must be on the top of the last conversion factor. So we can start realizing, we'll go work backwards. We'll go from the final conversion factor will be miles to gallons, and we know that we're trying to get to gallons then. And gallons is a volume, so gallons might be related to milliliters, which is in one of our conversion factors. We also know that we need to get to grams because that's also in one of our conversion factors of density. So we're kind of working our way in. So we'll go from kilograms to grams, grams to milliliters, and then we need to get from milliliters to gallons, and then gallons to miles. So notice that we end up having quite a few conversion factors in here. So we have a strategy, we're finally ready to plug in the actual values, some of which have to be looked up, and we can get to 1,024 miles. Here's one that looks more like an actual dosing question. To prevent bacterial infection, a doctor orders 4 tablets of amoxicillin per day for 10 days. If each tablet contains 250 milligrams of amoxicillin, how many grams of amoxicillin will the patient ingest over the 10 days? So we need grams of amoxicillin. We're told 4 tablets of amoxicillin per day. We're told a total of 10 days, and we're told that each tablet has 250 milligrams of amoxicillin. I should also say that it wants grams amoxicillin in the 10 days. So we should probably begin with the 10 days. That seems to be the starting measurement. 4 tablets per day is the conversion factor, and tablet has 250 milligrams is an equality between 1 tablet and 250 milligrams. So both of those would be conversion factors. So let's set up our conversion factors and realize that we could either use 4 tablets per day, or 1 day per 4 tablets, or 1 tablet per 250 milligrams, or 250 milligrams per 1 tablet. So if we begin with 10 days, we know we need days on the bottom of the first conversion factor, so we'll choose the tablets to days first as the first conversion factor. And then we can go from tablets to milligrams, and then from milligrams to grams. So we're putting in our units, devising our strategy. Finally, we can put in our numbers. 4 tablets per 1 day, 250 milligrams is equal to 1 tablet, and 1 gram is equal to 1,000 milligrams. And realize it's 10 grams. So as we get to more complicated dosage problems, many of them have several per in it. We want to put all of those that say anytime you see the word per, it means in the denominator of that first conversion factor. So 20 milligrams per kilogram per day would look like this. And recognize that there are 2 mass units here, milligrams and kilograms. And it's really important, this happens often, that the client's dosing is related to the client's weight and the medicine's weight. So you cannot compare them because the milligrams is referring to the medicine and the kilogram is referring to the patient. And if that confuses you, you would want to probably identify next to the milligrams that the milligrams is referring to milligrams of medicine and the kilograms is referring to kilograms of a patient. Obviously, you would not want to confuse them, or else you'd have a very severe difference in dosing. So let's look at this problem. The healthcare provider prescribes amoxicillin 50 milligrams orally every 8 hours for a 15-pound client. The medicine contains 50 milligrams per milliliter. The recommended dosage is 20 to 40 milligrams per kilogram per day in divided doses every 8 hours. How many milliliters will be administered in one dose? And is it in the recommended range? Well, first let's recognize this is two separate questions. The first question is asking for milliliters in one dose that's been prescribed. The second question is asking, is the milliliters in the recommended range? Looking at what we're given 50 milligrams of amoxicillin per 8 hours. That's a conversion factor. We're also told one dose is equal to 8 hours, since they're telling us that it's going to be doses every 8 hours. We're also given it's a 15-pound client. We're also told that it's 50 milligrams of amoxicillin per milligram of medicine, milliliter of medicine. And then we're given the recommended dosing of 20 to 40 milligrams per kilogram per day. And again, per kilogram per day would mean that both of those would be on the bottom of the conversion factor. So we will begin by taking the prescribed milligrams per 8-hour milliliter to milliliters per dose. So we would start with 50 milligrams of amoxicillin per 8 hours. That's what was given. And we're trying to get to milliliters of medicine per one dose. So we can devise a strategy. Since hours are on the bottom, we need something to go. So we'll find something that would have hours on the top. And the only other thing that we have is relating hours and dose. So hours on the top, dose on the bottom, and it would be 8 hours per dose. The second conversion factor is going to use the milligrams and milliliters conversion. Since we have 50 milligrams of amoxicillin in our starting starting factor, we're going to put the milligrams of amoxicillin units on the bottom of the second conversion factor, and we'll put the milliliter of medicine on the top. And from this, we recognize that it turns out to be 1 milliliter of medicine per dose. The second question is a little bit trickier. We now have to compare milligrams per dose to the milligrams per kilogram per day. So we have to have the same units in order to actually make a comparison. So in this case, we're going to take the recommended information and convert it from milligrams to dose, although we could go the other direction. So we'll begin using 20 milligrams per kilogram today, the lower end. This is a little tricky. I know that that this is all related to the client's weight. So with a little strategy, I can recognize that I'm going to begin with 15 pounds because that's the client's weight. I'm going to have to get that into kilograms because the dosing is milligrams per kilogram of patient. So I'm going to use a kilogram to pound conversion. And then I have my recommended amount, 20 milligrams per kilogram per day. I have to recognize that there are 3 doses per day. Of course, I could have said that there is 1 dose per 8 hours and 8 hours or 24 hours in a day, but I just used some math and said there's 1 day is going to be 3 doses. And so if I do this conversion, I find out that for a 15-pound client, the minimum recommended amount would be 45.5 milligrams per dose, which is, that is below 50 milligrams per dose. And then I have using the 40 milligrams per kilogram per day conversion factor. The conversion is set up exactly the same, but it would turn out to be 90 milligrams per dose. So now I can make a comparison. Our original, what was given in the original problem was that it was 50 milligrams of amoxicillin per 8 hours, but 8 hours was 1 dose. So that's 50 milligrams per dose. and that's in between the 45.5 milligrams per dose and the 90 milligrams per dose. So this would be safe because it's below the maximum, and therapeutic because it's above the minimum. Note that a slightly different strategy would have said, let's take the prescribed dosing and convert it to the dosing that we were given in the recommended amount, which is milligrams per kilogram per day. So the problem starts off the same, but on the second question, we're going to take that 50 milligrams of amoxicillin per dose, and that's going to be my starting information, and I'm going to try and convert it to units of milligrams per kilogram per day up on the right-hand side. Notice that I recognize dose as a unit of time, that's why I've circled it in green, and day is a unit of time, so I just have to convert between dose and day for that. The milligrams is staying the same, milligrams of amoxicillin, but notice that I have kilograms on the bottom of the final factor, so I recognize the kilograms is referring to patient weight, so I'm going to have to somehow pull in that 15 pounds of the patient. And what I will do is I will begin with the 50 milligrams of amoxicillin per dose, and I'm going to divide by the 15 pounds of the client's weight so that I can get that weight unit in the final units. And then I have to do some conversion. Now that I recognize pounds are on the bottom, I'm going to want a conversion factor with pounds on the top, kilograms on the bottom, and I look up those numbers. I also need to convert from time units of dose to time units of day, and I know that there are 3 doses in a day. Again, since I start with dose on the bottom of the starting factor, I'm going to want a conversion factor with dose units on the top of the conversion factor so that they can cancel. And then I'll put day on the bottom, and I'll fill in that it's 3 doses per day. And when I complete the calculation, I get a prescribed dosing of 22 milligrams per kilogram per day for this 15-pound client, which is in between that 20 and 40 milligrams per kilogram per day, so it is therapeutic and safe. So you see, as these questions get more tricky, it's still the same general strategies that we've been using for those easier problems. Just work out the units, pay attention, set your units up, your word problem into your right conversion factor so that you know what units you're really working with, and slowly proceed through and you will get this.